Hello, all. This is Corey Arnouts, and this is my master's thesis for my master's in data science. So, essentially, what my paper is it's titled Process Mining to Aid in the Claims Litigation Predictive Modeling Process, and I'm focused here on insurance, specifically personal auto insurance. And then within personal auto insurance, I'm looking at a coverage known as personal injury protection. This is a unique auto insurance coverage in the fact that that auto insurers have to pay for almost all the costs of injuries associated with an auto accident. And this is really kind of specific to Michigan for the most part. Michigan has pretty unique high limits for personal injury protection, so the auto insurers are actually the ones covering a lot of the healthcare costs associated with injuries that occur in auto accidents, as opposed to other states where there might be a lot more coordination or a lot more of those bills that are taken on by their health insurance company. So up until recently, Michigan was actually a no-fault state and had unlimited limits on personal injury protection insurance. This meant no matter how high the cost of the claim, the medical coverage did not cease. The insurer had to pay as much as the costs were. There could be claims that go on for 20, 30 years, depending on how bad the accident was, long-term care, those sorts of things. But because of these unlimited limits, a lot of medical providers could take advantage of this. In Michigan, it's pretty common to see, if you go into an emergency room, if they'll ask if the injury or ailment or injury normally related to an auto accident. And if you check yes, that actually will invoke a whole system of kind of different billing and those sorts of things, just because um, their billing system is different, or their billing systems of billing are different for auto related accidents because of the personal injury protection. And because a lot of these medical providers have better relationships with health insurance companies, there's also set rates on different things, and those sort of things didn't exist, or don't exist, and are starting to exist, but don't really exist in Michigan right now. So, like, a lot of times, there might be an MRI, for an example, for an auto-related injury might be as much as 10 grand, where for just a regular non-auto related injury might only cost $1,000 at the same place. And this is because these medical providers know that they can get more money out of the auto insurance companies, so they're going to take advantage of that. So really, these really can become astronomical costs for these PIP claims. And what eventually happens is the insurers may refuse to pay these unreasonable prices, and then the claim will end up in litigation, essentially a legal battle between the medical provider and the insurance company. And so, when this happens, insurers then have to go to court and still might be stuck with the full cost of medical bills and legal bills. So it just makes claims a lot trickier. So we really want to avoid litigation, or at least know what claims potentially might have the potential to go into litigation, to see if we can steer those claims, because maybe there's claims we know are definitely going to be litigated, and we would prefer not to pay anything on them until it's all settled in court, because maybe we pay half the costs. We're not going to get that money back. So, even if we win the case, some of the money that we already paid is off the table. So it's really about having a coordinating strategy with these different types of PIP claims. So I'm focused on Farm Bureau, Michigan. That's where I work. They have taken actions up until this point to reduce costs and inspect suspicious claims early in the claims life cycle, but many of the efforts have not been as coordinated and data-driven as possible, or as they could be. And through the use of analytical techniques, new methodologies, and a lot of the stuff I'll present in the paper today, I'm really looking to overhaul this system of business processes that are dealing with these claims, specifically PIP claims. And in order to do this, we really need to understand the claim life cycle. One field that's really helpful in doing this is process mining. This is a type of analysis that uses event logs from information systems to look at how processes play out from a data perspective. using event log data, organizations discover how processes are actually being executed and then can optimize these processes. And then going into what predictive modeling is, it uses data from the past to predict what's going to happen in the future with statistical models. It has a rich history in the auto insurance space for loss forecasting, along with other things. But to a large degree, predictive modeling in the insurance space is based off of static modeling elements such as loss history, age of insured, type of vehicle, size of home, insurance score, some of these different types of metrics. What I'm actually looking to do is to bring into some more dynamic metrics into these predictive models or into the PIP litigation predictive model. And these process-based features are going to be more dynamic and informative, making decisions not based off just static elements like the age of the insured and location, but on actual actions that the insureds and the customers are taking. Process-based feature engineering will allow insurance companies to understand the way the clients are interacting with our goods and services. Some of the key words are process mining, discipline of extracting insights from process data; process trace, that's a specific path that a process can follow; process instance, it's a single iteration of a process; predictive modeling, algorithms that use data from the past to make predictions; claims litigation, lawsuits involving insurance claims; personal injury protection, component of automobile auto insurance that covers healthcare expenses associated with a car accident; provider network metrics, so this one I'll get into a little bit later as well. These are statistically derived metrics around the proclivity of certain medical providers to end up in legal battles. Household metrics, these are more on the client side. These are measures of profitability of customers and can be thought of as a more holistic view of a customer. As they bring in more data from different lines of business, different members of the household, that sort of thing. And then gradient boosting machine, this is one of the machine learning methods that I'll use. It uses tree-based weak learners to make predictions, measures an error function, and then uses subsequent models to reduce the error. That's where the boosting comes in. My problem statement is to create a predictive model that will predict with a high degree of accuracy whether personal injury protection claims will end up in litigation. I'm making a prediction based off the information that is available on the claims within 60 days of the claim being reported or before the litigation takes place. I also developed some models that look at what a day one prediction on claims litigation would look like. I build the training set off of 2016 through 2018 data and then build testing data off the first half of 2019. There's a little bit, some of it you might say, well, that's older data. And the reason for that is because the litigation has to have time to actually develop on these claims. If I do 2020 claims, a lot of them won't have essentially the chance or the opportunity to go to litigation yet. These things develop over longer spans of time. And my objectives to prove that the predictive model can be useful and predictive. Some of the related work I look into. I talk about process mining. It was started by Will van der Eest. He's a computer scientist as a way to understand and visualize processes. There is some different work being done that kind of combines predictive modeling or machine learning and process mining. Talks about discrete event transition probabilities within event logs to predict specific process outcomes, which is essentially what I'm trying to do here. And there's other instances, a lot of good work in this area. It shows how different advanced modeling techniques can be applied to predict process outcomes. It's kind of this convergence of process mining, looking at process data, and machine learning is definitely, early in its maturity cycle, but they're both very interesting technologies that have been traditionally viewed as separate, but I think it's pretty cool, the convergence of the two. And then also I discussed some research that's available around network-based metrics that can improve predictive models and social network analysis, showing and highlighting highly irregular behaviors that can be helpful for predicting target variables. And I engineer some features off of this too a little bit later. So for my data gathering process, I get data from all across the enterprise, all different systems. Here you see I use KNIME, which is a data science platform, to go and get all of this data. I actually have KNIME open, and let's see. And so here is my PIP predictive model. So it aggregates data from a lot of different places and then ends up doing an R script at the end. But all this is data aggregation and data moving from different databases, connects to a database, queries said database, and then moves that data onto kind of a common server that I use. And then the R script brings all of it in at the end. Excuse me. So it's pretty cool stuff. It's a good way to kind of do all your ETL processes in one place, your full kind of data science workflow. And yeah, so it's pretty cool. And then see here at the end, that's where the actual R node is that executes code as well. So kind of combines SQL and R. It can combine Python. It has its own tools as well. It's pretty cool. It's a pretty cool platform that I use for a lot of my work. So back to the paper. So that's kind of what I show off here and bring in different attributes from across the enterprise, different servers housed in different locations. Use it for SQL and R in this case. It kind of orchestrates all of it, all the data science stuff together. Here I talk a little bit about the process-oriented data, process mining, what data you need. You need a case ID that ties the process data together. You need activities and events, and then timestamps to essentially show the order. So here's kind of a simple version of I have the claim number blocked out here of what it might look like. Initially, you have activities and then timestamps, and then they're tied to a case. And then here I show a transformation that I do where I essentially say, all right, what order did the activities appear in? So you see essentially what they'd call discrete event transitions from one activity to another. So going from, assignment to first notice of loss, or contacting the insured to contact the insured, so insured contact twice in a row, or settlement to receive police report. So these are all different discrete activities that occur, and we're looking at the transitions between the two, and then we actually pair this up with our target variable, which is the litigation indicator showing whether or not this claim eventually ended up in litigation, and then we aggregate across all of these discrete event transitions to come up with a process transition matrix that shows what paths taken are relevant, or what paths are taken for claims that go to litigation as kind of a percentage. And then so for for feature engineering, I start to discuss some features. Like I said, process-oriented metrics, target meeting coding, discrete event transitions. So I kind of talk about it here a little bit more. This is kind of like what a process mining map would actually look like. I'll zoom in. So you can see here transitions from different discrete events or activities, and then the different paths have numbers on them, and that represents the percent of those claims that travel that path that ended up in litigation. So we would calculate a metric that for a claim that took this path, we would add up all these transition probabilities. So we have this is a 0.17, 0.17, 0.1, 0.1, and then take the average of those for 0.135. So that would be the metric that would be the actual metric for that claim. It would have a 0.135 process-based metric, however, I forget how I word it exactly, a process-based litigation encoding. So based off the claims path only, it has a 13.5% chance of going to litigation. Again, this is kind of like a rough estimate. It's probably actually maybe higher than that, but the predictive model at the end kind of takes all that data and chews on it in the most effective way anyway. So it can kind of be interpreted that way. I don't necessarily recommend directly interpreting it that way, but definitely the higher the number, the higher the likelihood of litigation based off of the claims path. And again, these are just different events that occur within the claims life cycle, taken from data within our admin system. So we'll talk about engineering process-based features. This kind of shows a broader transition matrix across a lot of different activities. Now, this isn't everything, but it's a lot of stuff. And yeah, so you can kind of see like some of these like medical issues to coverage has like a really, really high process-based metric. And it makes sense, if you have medical issues and then something about coverage, you're probably something's tricky going on about that claim. But some of these paths, new claim to contact with the insured, a really low litigation proclivity. This is pretty like plain Jane, like common path that's taken by a claim and is not indicative of litigation really at all. The base rate for litigation is around 11-12%, so that's about the average amount of claims that go to litigation. So those are that's some of the process-based metrics that I incorporate into the model. Now I'll get into some other features. Here is the household metrics. So these are metrics that are based on a 360-degree view of a client. Knowing as much about customers as possible is a great way to make business decisions. And essentially, I view as much history we have about different clients in the household that they're a part of. So this kind of shows it off. This is a household with 4 people. There's 4 contacts involved, and then they're on 4 different policies, but you can see different people are connected to different policies. So all the policies are taken into account. You have the standardized loss count proclivities. So these are relative to expected. So 0 would mean you had exactly the expected amount of claims, and this is for the entire life of the policy essentially. So let's say we expect 1 auto claim every 5 years, and you've had your auto policy for 5 years and you've had 1 claim, that you would get a 0. So it's relative to expected. It's essentially a z-score that shows relative to what we'd expect, how many losses do you have for said policy. Excuse me. And then you aggregate this across all the policies in the household, and then you come up with kind of the household standardized relative loss count. And so this is a metric for how likely, or how, what kind of proclivity does your household have to have losses? Like, do you have losses more than expected, less than expected, kind of on a higher level? So that's the loss count, and then I go into other ones talking about their relative premium compared to what would be expected, their loss amount, and this shows kind of the effectiveness of these household features. So this is household loss amount, and if you have less losses than expected, then you have a lot less of a litigation percentage likelihood. And if you have more household losses than expected, then you have a much higher litigation proclivity. So it just shows how, and this is all historical data. It's before the loss that the data, this data is built off of before the loss that we're bringing it in for the analysis for. So you can tell that, households that are quote unquote bad are proved to have more litigation, and so these are kind of good metrics to use to predict litigation based off of how this client has behaved in the past. Brief explanation of data leakage. So as you can see, like in my process-based features up here, I do encode some of the target variable. But there is some data leakage in the training set, but there was no data leakage in the testing set, because all of the kind of process encoding is built just off of the training set, and then those features are used for both the testing and training set. So the training set has some data leakage or target variable leakage, but the testing set does not. So we know that performance is generalizable. Claims contact and healthcare provider metrics. These are metrics around the actual providers that are on the claim and the number of lawsuits that they've had in the past. So here you can see you have different claims. They're connected to different providers that provide medical service for the injuries incurred on these claims. And then you have, litigation as a result of this activity. And you can see different providers, depending on the number of claims they're on, litigation or provider one's on 1 claim, 1 lawsuit. They'd have 1 provider lawsuit proclivity. In reality, these numbers are much higher as far as the number of claims, number of lawsuits. Provider 5 has 2 claims, no lawsuits, so zero provider lawsuit proclivity. And then essentially we score each provider and then take the average of those providers across for each claim. And so if a claim had providers 1, 3, and 5, they would have a 0.61 provider lawsuit average, essentially. And this is a good predictive feature as well. And again, there's a little bit of data leakage in the training set because some of the target variable that you're encoding, you're also predicting. But there's not for the testing set because none of that data is used for this encoding of, what providers have had how many lawsuits. And then we take a look at the predictive power of this. And as you can see, the higher, this is the provider lawsuit proclivity average, the higher that is. So the more that the providers you have on your claim have had lawsuits in the past, the more likely you are to have a lawsuit on your claim, which makes a lot of sense because a lot of this activity is driven off kind of the same network of providers who are constantly, suing insurance companies. Medical review data. So this is actually data around the services, the medical services that happen. And this one's actually taking a look at the date of service, the first date of service. So did you get service the day that the claim happened or after or even before the loss happened? And you can kind of see the litigation rates according to when you got your first medical service after the claim. There's actually a handful of claims that have a service before loss. And so you can know if you actually went to the doctor about an injury you didn't get yet. You can tell that that's pretty suspicious, and a lot of these do end up in litigation. But also, kind of a service on loss is not as high of a litigation rate, but then service 2 or more days after a loss is also pretty suspicious because why did you wait that long to go get medical service? So a lot of those end up in litigation as well. Geospatial analysis of essentially what types of claims based off their loss location end up in litigation. And you can kind of see it's in the southeast region here. And it's really kind of in this Warren, Sterling Heights area. This is looking at census tracts. I show you a sample decision tree down here based off the Latin logs. And this is essentially the segment that the decision tree is looking at. Basically saying that claims in here have, a really high, 0.3, 30% loss or litigation proclivity. So just based off loss location, you can really tell what claims might be more likely to go to litigation. Also use insured age as predictor variable. You can kind of see, depending on their age, about 60 to 75-year-olds are much more likely. This is the distribution of claims that went to litigation in blue and the distribution of claims that did not go to litigation in red. So you can see that kind of the blue where the difference is, like that 60 to 70 range is really where a lot of those go to litigation. People's driving ability starts to decline at this point. They might be more susceptible to really bad injuries that might, then cause a litigation to happen. It's kind of hard to say, but some interesting, patterns there. Building the predictive model. Fix that. Okay. So I gather and prep all this data together, kind of construct the test set. For the test set, I don't use like a 70-30 split. Like I said, I actually use, data up until 2019 for the training and then data of the first half of 2019 for the test set to see if it'll kind of generalize over time. I did a random forest, logistic regression, a ranger random forest, a gradient boosting machine, and a day one gradient boosting machine, which is essentially just using certain variables, loss location, age of insured, and household attributes, because these would be available day one of the claim. And I wanted to see how well a model would do that would predict litigation on day one, because the other stuff is built off of day 60 of the claim, so we've had some time to watch the claim develop and gather some of that data. And as you can see, the two top performing models are the Ranger Random Forest and the Gradient Boosting Machine in green and purple here. Both do really, really well. The red one on bottom here is the day one model, but you can still see it has quite a bit of lift above average, so it would do better than we're doing today, because today we don't have any rhyme or reason on how claims get assigned, really. And then evaluating the model results. So the 60-day model, you can see, for the top 5% of top 5% of highest scoring claims, the efficiency multiplier is about 6.19. So that means in this top 5%, you'll find roughly, 66, close to 70% of claims actually go into litigation. 31% of total litigation is found in just these top 5% of highest scoring claims. So you could, send these to a litigation specialist right off the bat, and we would be in much better shape to handle that claim. Or I guess at the 60-day mark, because that's when this model is being ran, but you could reassign those at the 60-day mark to a litigation specialist, and they're more equipped, a better equipped resource to handle these types of claims. So this really gives you a sense of how well it is at predicting. I kind of use these percentiles because, this is how claims would be assigned. Depending on their score, they'd be triaged to certain people depending on their litigation proclivity, essentially. Looking at some variable importances, excuse me. One of the most important variables is distinct service date count. So this is the number of services that you had in that first 60 days. Some other ones are that provider lawsuit average that we looked at, Latin longitude, loss location type stuff, process lit rate, that's that process kind of based mean or target variable encoding that I talked about based off the discrete event transitions. And then total bill count, the number of total bills you got in the first 60 days. All this is based off the first 60 days. Some of those household attributes that we talked about end up in there, the insured age. And so, yeah, it performed well. Like I said, it does a really good job. The the ROC is 0.88. So, it does a really good job above what random selection would do. At identifying what claims are going to end up in litigation. The top 5% highest scoring claims represent 32% of the claims that went to litigation. The top half of the highest scoring claims represent almost all the claims that go to litigation. So you have almost half the claims off the bat you can just ignore as far as their risk to go to litigation. So, yeah, pretty cool stuff. And I also come up with a day one model I show off here that's kind of developed just off of those household features, loss location, age of insured, the stuff that you would know day one. And so I think actually I have these flip-flop. Okay. Yep. So this is the day one model at, it still finds 22% of the litigation in the top 5% and 40% of the litigation in the top 10%. So it still does pretty good. And you could triage these claims right away, which is the nice part, is you don't have to wait. So this would be maybe even a more useful model because you can move these claims and triage them right away. So in summary, the initiative predict which PIP claims will end up in litigation was successful. We see the predictive model performs many multiples better than random. And, there's this hopefully will be implemented here soon. There's more technological improvements coming to this process, and we hope that we can kind of bake this in with some of these process overhauls and facilitate the triage early in the claim to get the claim in the hands of people that should be handling them. There's also certain actions that being taken on these claims. If we think they're going to go to litigation, maybe we get an independent medical examination done on them earlier. This is where we kind of have someone, a doctor that we trust, go in and examine the injured party. And so to kind of take it another step, and this is also a component of process mining, we can look at all the events that are happening on this claim and then start to decide how we want to alter the process and how we actually want to develop a strategy. So once we develop a strategy for handling these claims, we can see through process mining the conformance to said strategy. And this is from a dashboard that I built in Tableau. It's a process mining app that's available in Tableau where you're able to monitor your processes kind of real time and see what's going on. So this is just kind of a screenshot. But you can see if these claims are actually being handled the way we want them to be, which is pretty cool. And will help us kind of come up with this coordinated strategy that we're really hoping to do here. And so that is about it. This is the script. I made it available, all the data available out on GitHub, and then I hashed the claim numbers, so there is, no internal data. All the other features aren't, PII or anything that's identifiable to an individual, and all the claim numbers are hashed, so they're not what we use. Um, and so yeah, try out a few different models that I described, and then I look at the results at the end. And a lot of the visualizations were also done in Tableau, kind of mixed between Tableau and R. But it was a good project, and I think it'll hopefully be implemented into our systems in one way or another. And yeah, I got to use kind of a lot of my culmination of knowledge that I've gained across this program. So appreciate the opportunity, and thanks for listening, everyone.